You know, from the phone that's probably in your hand right now, to the Wi-Fi router in your house, our entire modern life is built on these invisible signals. They're just flying through the air around us. We depend on this stuff completely, but for most of us, how it all actually works is a total black box. So, let's change that. We're going to dive in and pull back the curtain on the magic of wireless communication.
Here's how we're going to tackle this. We're going to start from the very beginning, looking at the invisible highway these signals use. Then, we'll figure out how we get them to speak our digital language of ones and zeros. After that, we'll untangle the chaos of millions of devices trying to talk at once, and we'll look at the actual physical grid that makes it all possible. We'll even race through the evolution from clunky 2G to lightning-fast 5G. And finally, we'll touch on those other wireless heroes you use every day.
So, first things first, we have to start with the most basic question of all. What exactly is this invisible highway? How can something as complex as a video stream just fly through empty space from a tower to your phone? The answer to this is the bedrock for everything else we're going to talk about.
And the answer is electromagnetic waves. They are everywhere, and they are a fundamental force of nature. Your car radio, your GPS, your phone, every single wireless device you own works by sending and receiving these waves. And this isn't some weird man-made thing. It's a huge spectrum of energy that includes the very light that lets you see, but also the invisible radio waves we've learned to harness for communication.
Now, here's the cool part. All of these waves travel at the same speed, the speed of light. And because of that, there's a really simple but super important trade-off. If a wave has a high frequency, meaning its peaks are all scrunched up close together, it has to have a short wavelength. These are the high-energy waves, like X-rays. But on the flip side, a low-frequency wave with long, lazy peaks has a really long wavelength and carries less energy. And those are the kinds of radio waves that are just perfect for communication. They're what we call inversely proportional.
So when we talk about measuring that frequency, the unit we use is hertz, or Hz. And 1 hertz is just 1 cycle or 1 wave per second. You're actually totally familiar with this. When you tune your car radio to, say, 101.1 FM, what you're really doing is telling your radio to listen for a wave that is vibrating 101.1 million times every second. That's a megahertz. Our phones and Wi-Fi just take that to the next level, operating in the billions of cycles per second, the gigahertz range.
Okay, so we've got our highway. We understand that these electromagnetic waves exist. But a blank, empty wave doesn't carry any information, right? It's just a silent carrier. So the next big puzzle is, how do we get our data, our photos, our texts, our ones and zeros, onto that highway? How do we make a simple wave carry a really complex conversation?
Well, the process is called modulation. And the idea is actually pretty simple. You take a nice, clean, consistent wave, called a carrier wave, and you start changing it in a very specific pattern that represents your data. You already know the two most famous examples. AM radio works by changing the wave's amplitude. That's its height or power. And FM radio works by changing its frequency. Our modern digital devices use way more complicated methods, but the core idea is exactly the same. We encode information by tweaking the wave.
But what about interference? Static? To make our signals tougher and more reliable, we use this really clever set of techniques called spread spectrum. Instead of just sending our signal on one narrow frequency, we spread it out. One way is called frequency hopping. It's like a spy who quickly flips between dozens of radio stations to deliver a coded message. If one of those stations is full of static, you only lose one tiny piece of the message. The other way, direct sequencing, is like taking one song and singing it very loudly across a whole bunch of channels at once. It makes the signal really stand out from any background noise and lets you send data much faster.
Now let's talk about the big one, the technology that really makes modern high-speed networks like 4G and 5G even possible. It is a mouthful: orthogonal frequency division multiplexing, or just OFDM. The absolute genius of OFDM is this. Instead of trying to shove all our data down one single massive highway, it splits that highway into thousands of tiny parallel lanes. This makes the whole system incredibly efficient and tough. If one of those lanes gets a pothole from some interference, who cares? The rest of the data just keeps on flowing in the other lanes. It's how we can pack so much information into the airwaves so reliably.
So, we've figured out how to get one signal from point A to point B. That's great. But in the real world, you're not the only one using your phone. You're in a city with millions of other people all trying to talk to the same cell towers at the same time. How on earth do we stop that from becoming a complete mess of signals just shouting over each other?
This is what engineers call the multiple access problem. And to solve it, they came up with 3 main strategies. You can think of them as 3 different sets of rules for having a polite conversation in a super crowded room. We've got frequency division, time division, and the really clever one, code division multiple access.
All right, the first two are pretty easy to get your head around. FDMA, which stands for frequency division, is like telling every singer in a choir that they get their own unique musical note to sing. Everyone can sing at the exact same time, but because they're on different pitches, or frequencies, they don't get in each other's way. Then you have TDMA, or time division. This was the foundation for 2G networks. In this choir, all the singers have to share the same note, but they take incredibly fast turns singing their part. We're talking microseconds here, so to us, it all just sounds like one continuous conversation.
But the third method, CDMA, this is where things get really smart. With CDMA, everybody talks on the exact same frequency at the exact same time. Now, how is that even possible? Well, the magic is that each conversation is scrambled with a unique mathematical code. Your phone knows your code, and it can listen to this entire jumble of signals and perfectly pull out just the one meant for you. It's kind of like being in a massive party where everyone is speaking a different language. You can only understand the one person speaking your language, and everyone else just fades into unintelligible background noise.
So we've covered the physics of the signals themselves, but of course, these signals don't just appear out of thin air. They're part of a huge physical infrastructure that covers the globe. So let's zoom out and look at how the actual cellular grid is built, piece by piece.
You've heard the term cell phone your whole life, right? Well, this is literally where that name comes from. The core idea is to take a huge geographic area and chop it up into a grid of smaller zones or cells. Each cell is served by its own antenna. And these cells come in all shapes and sizes. You've got massive macro cells for covering wide-open rural areas, smaller microcells for dense cities, tiny picocells for inside a single building or a tunnel, and even femtocells that are small enough to cover just one house.
Okay, so when your phone makes a connection, it's actually following a whole chain of command. First, it talks directly to a BTS, the base transceiver station. That's the actual antenna on the tower. That tower is like an employee, and it's managed by a BSC, or base station controller. Think of the BSC as the office manager, juggling a bunch of towers at once. The BSC then reports up to the MSC, the mobile switching center. This is the regional headquarters. It's the brain of the network, routing all the calls and data. And finally, you have the HLR, or home location register. That's like the central HR department, a giant database that knows who you are, where you are, and what services you pay for.
Now, one of the most exciting things about cellular tech is that it never, ever stands still. It's defined by this relentless, rapid evolution. Each new G, or generation, marks a huge leap forward in what's possible, and it changes not just the tech, but how we all live. So let's play the generations game.
And man, has it been fast. Back in the early 90s, 2G was a revolution. It gave us clear digital calls and the absolute magic of sending an SMS text message. Then around 2001, 3G came along and made the mobile internet a real thing, even if it was painfully slow at first. Then came 4G around 2009, and that gave us the true high-speed experience we take for granted now. It enabled video streaming and the entire App Store economy. And now, 5G is pushing those boundaries all over again with mind-blowing speeds and almost zero lag, opening the door for the true Internet of Things.
Now here's something really crucial to understand. These different technologies all run on specific radio frequency bands, and those bands are not the same all over the world. For example, a common 4G band for rural coverage in the US is down at 700 MHz, but the standard in Europe is way up at 1800 MHz. This is exactly why your phone needs to be a multi-band phone to work when you travel. It has to be able to speak all these different frequency languages.
And the leap to 5G, it's just staggering. The peak theoretical speed is 20 gigabits per second. Just to put that into perspective, that is fast enough to download a full, feature-length 4K movie in just a couple of seconds. But this isn't just about faster downloads. This kind of speed, combined with almost no delay, means 5G can actually replace your home cable internet provider and, maybe more importantly, become the nervous system for the Internet of Things, connecting smart cars, smart cities, and all kinds of sensors in real time.
Of course, cellular isn't the only wireless game in town. We've spent a lot of time on it, but we all rely on a couple of other crucial connections that are built for very different jobs. Let's wrap up by looking at the other pieces of the wireless puzzle: Wi-Fi and Bluetooth.
I absolutely love this analogy because it makes the difference between these two crystal clear. Wi-Fi's primary job is networking. It connects your devices to the internet. Just think of it as a wireless replacement for that old Ethernet cable. Bluetooth's job is totally different. It connects devices to each other over a very short range,
like your headphones to your phone or a keyboard to your computer. So you can think of it as a wireless replacement for a USB cable. They're two different tools for two very different jobs.
And just like the cellular world, Wi-Fi security has had to constantly evolve to keep up with threats. We started with something called WEP, which turned out to be so insecure it was like leaving your front door wide open. That led to improvements with WPA and then WPA2, which has been the solid, reliable standard for years. But the latest is WPA3, and it's a really important upgrade. It's much better at protecting against password-guessing attacks, and, get this, it automatically encrypts your connection even on open public Wi-Fi, like at a coffee shop. That's a huge deal for your privacy.
So there you have it. From the basic physics of a radio wave to the incredibly complex global grid of 5G and that personal bubble of Bluetooth around you, we are living in a world that is completely wrapped in a constant, invisible conversation. We've seen how far it's all come in just a handful of decades, which really only leaves one question. What will the next conversation look like?